I'm going to talk about something very simple, gravitational cat state. I'm sure most of you know what a cat state is. You're way too sophisticated in quantum information, and I'm just trying to add in this gravitational aspect. As we all know, it's unavoidable because all events take place in space-time. And of course, space-time is Einstein's way of understanding gravity. So this is really a basic element, the way I look at it, when one begins to bring in quantum information concerns in a more general context. In fact, it's not more general, but in a necessary context, which is space-time and gravitational effects. So those three elements are, of course, quantum information and gravity. I was told to use this thing. All right. So quantum, I think a lot of discussion here is based on quantum mechanics. The way I look at some of the controversies in terms of non-locality, causality, causation, superluminal signaling, etc., I think there won't be that many puzzles if you care to just elevate the level to quantum field theory. Okay, that's the only remark I'll make. But for our purpose here, of course, that's the theory quite well established in the description of microscopic particle interactions. Whereas on the other hand, gravity, and we're going to stay actually in the framework of Newtonian mechanics for the purpose of this talk, but we also know that that really is a weak field limit of general relativity theory, which is also proven to be the accurate theory on the whole for macroscopic phenomena, as far as, of course, even the size of the universe. And if you care to bring these two fields together, well-proven fields together, that's semi-classical gravity. That's what it is. I'll say a little bit more about that theory because of the relevance to alternative quantum theories, such as the Newton-Schrödinger equation. Now, I've divided into the left side and the right side. In strong field conditions, actually, that is the arena that we've been working on in the last 30 years since the establishment of semi-classical gravity. Mainly, of course, you need to work with quantum field theory in curved space-time, and that was a theory quite well established already in the 70s, as shown, of course, for example, in Hawking radiation. Some of you may not realize that a very simple example of semi-classical gravity is in inflationary cosmology. The source of that is a simple expectation value of the Higgs field or the gauge field, but nonetheless, you are trying to solve the semi-classical Einstein equation with such quantum sources. And of course, we understand, we know a lot about inflation. So 1980 was really, in the 80s, inflationary cosmology, I would say, is a very good example of semi-classical gravity. Now, our attention here in this talk and in more recent years is really in weak field non-relativistic limit accessible by laboratory experiments. And of course, there's also, in the past 10 years, more than that, the ongoing work in analog gravity, which you'll hear some in Silky's talk following this. So I mentioned semi-classical Einstein equation, and then there's the question of where does the Schrödinger-Newton equation come in. In my talk, I'm not going to focus on that because I like to focus more on the quantum information aspect of it. But I'll just say that there are two layers of theoretical construct, and one small surprise is that the Newton-Schrödinger equation for single or multiple particle is not derivable from quantum field theory plus general relativity, much to the surprise, well, myself included, because naturally you might think that Newton is, of course, the weak field limit of Einstein equation, and Schrödinger is the non-relativistic limit of quantum field theory. The key there is that so this is the Schrödinger equation. Let me switch over to here. If you take a look at the structure of semi-classical gravity theory based on the semi-classical Einstein equation, this is just the classical energy momentum tensor, which already has given you the standard model of all things. We're talking about the vacuum expectation value of the stress energy tensor, and that's what this little q is, and the angular bracket refers to taking the expectation value, usually it's the vacuum expectation value of the stress energy tensor of some quantum field as the matter source that drives the space-time dynamics, okay? So the key there is that, if you just solve this equation, let's just take a massive scalar field equation. That's quantum field theory in curved spacetime. The curved spacetime part, of course, comes in the Laplace-Beltrami operator. This box operator contains the metric function in there. That was the activities in the 70s. And now if you demand that the Einstein equation is driven by a quantum matter source, as I just mentioned, which of course propagates in the curved spacetime, and if you demand that that curved spacetime is a solution of this Einstein equation, that self-consistency actually is where the difficulty is in the solution of the semi-classical Einstein equation. Now, the third element is quantum information, right? So, of course, let's start with the most basic element, quantum entanglement. If we examine the expectation value, not respect to a vacuum state, as I just mentioned, where a lot of the work in the last 30 years have been carried out mainly in strong field conditions, like near the black hole horizon or in the early universe. But look at, for example, a cat state, okay? A cat state, gravitational cat state, basically is just two masses situated at -x and +x, let's say. And you can construct the entangled state, the Bell state, the left and the right, let's say, right? Well, semi-classical gravity is not sufficient for quantum information, because the prediction is that it's right at zero, which of course doesn't give you any information on the fact that actually the mass distribution is in plus or minus x, okay? So immediately, we know that this rather well established theory, semi-classical gravity, is of no avail if you want to ask questions in quantum information. All right, so what is needed is to include the contributions from the fluctuations in addition to the mean, right? Because if you just take the mean, then it's zero, plus x and minus x, average to zero, okay? You're not getting any information, and the first information actually is contained in fluctuations. We know the fluctuations actually is an equivalent way of expressing correlations. Even in fluctuation dissipation relation, there are two versions. One is in terms of fluctuations, the other is in terms of correlations. So it's no surprise, actually, it's really the correlations of the stress energy tensor, the Tmn, T mu nu, T rho sigma, is needed to address issues in quantum information with gravity. So that's the first statement, very simple and direct. But then you might ask, well, is there a theory that would incorporate this quantity? Indeed, there is such a theory, which was established actually in the early 90s. It's known as stochastic semi-classical gravity theory. And I want to emphasize here, whenever you see stochastic, like in alternative quantum theories, that's been going on for a long time also, since the 80s. The stochastic element usually is put in by hand. You say, well, here's a Schrödinger equation. Let's put in this, a noise source over there. For whatever justification, they're all well motivated, of course, right? You want the wave function to collapse right in front of your face at a certain scale, and you say, well, this stochastic source would do the job for you. I want to emphasize here that the stochastic element actually is not put in an ad hoc manner, and this is important to recognize. Everything comes out from, again, general relativity and quantum field theory. In fact, that's what puzzled me in the early 90s as to how you can indeed talk about, first of all, dissipation, okay, because everything is unitary. It's such a beautiful theory, Einstein's equation, all that. And now, you want more in addition to dissipation. You also want noise to be all incorporated in this marble palace, right, of the Einstein tensor on the left-hand side. And the only way to do it, of course, is from the right-hand side, the sandstone. You can actually do something with it. And it's waterproof and airtight, and that's why I think this is really a way to deal with quite a few issues. And let me just name one. Well, let me just describe what this theory is, only schematically, right? That's a term of the vacuum expectation value, or any quantum state, the expectation value taken with respect to any quantum state. What's added here is a stochastic term related to the quantum fluctuations of the stress energy tensor of the matter field, and is characterized by a quantity known as the noise kernel, which really is the expectation value of the two-point function, which I just mentioned, the T mu nu, T rho sigma, the Bei tensor. So it's two-point correlation function of the stress tensor, Bei tensor. And the average value is equal to 0, but the interesting thing, of course, always for these stochastic quantities are the correlation function. The correlation function is the noise kernel, and the noise kernel is simply just the expectation value of the stress energy by tensor, Bei tensor. So, and it's proven already in the 90s that this quantity is actually symmetric, traceless, divergence-free. So it obeys all the nice quantities and is covariant, and so it's nothing of the nature of that we're used to in characterizing any stochastic processes. Even though, well, this is really for those people who know a little bit more about it. It's thanks to the Feynman-Vernon identity that you can actually write a certain component of that in terms of influence functional, in terms of classical stochastic forcing term, okay? That's it. You don't need to even talk about noise if you don't like it, if you find it irksome. Just stick with the geometric aspect. Everything is fine, okay? Now, maybe I shouldn't go into too much details, but this is an example. If you take the just simple linear perturbation of a curved background metric G0, G mu nu 0 there, then you can write this out. There's a familiar term, of course, of the terms arising from the renormalization of quantum field, which of course enters through the Gauss-Bonnet identity, through the additional parameters here. This is the cosmological constant. I'm referring to the outcome of the renormalization of the quantum field, and there's also the alpha and beta terms there. So now what's of interest here is really this last term. And this gives rise to non-local dissipation, meaning that it's not a delta function when you characterize dissipation process, and also a color noise, because in general, it's not a white noise source. So again, okay, so the non-locality shows up here in terms of the non-Markovian property of the noise, and certainly stochasticity. As I mentioned, this theory since the 90s have been examined in connection to issues of strong field conditions, like in the early universe and black holes. Okay, let's move forward now, right? So, as I mentioned just 5 minutes ago, even looking at the weak field non-relativistic limit, so this is for real, this is what can be tested and should be tested out. It's not like near the black hole horizon or the early universe. You can say, well, why do I care, right? Well, okay, one day maybe we could, through analog gravity, we could actually say something about those strong field conditions. But this is really bringing it home, okay, right here. So this should be the canon for all alternative quantum theories invoking stochastic sources. So what I was referring to is that the least one should do is to take the Einstein-Langevin equation and then look at the ramifications, the consequences thereof. That is a natural source there associated with the quantum matter field. And some recent work of T.P. Singh had followed up that line of development. So back to quantum information. Okay, so in gravitational quantum physics, the new emphasis is not vacuum state, but one particle, and it's not, one particle or n particle states, which we could work out nicely. Well, in fact, squeeze state, for example, is the state that we have after cosmological expansion, cosmological particle production. But what we want is a quantum superposition state. Let's say start with the cat state, okay? All right, so the first part, the take-home message is in green here. Look for gravitational quantum cat from the fluctuations of energy density or the correlator of the stress energy tensor, otherwise known as the noise kernel. All right, I'll go through this a little bit quickly to get to the point where we could look at how to probe a gravitational cat state that's more meaningful operationally. What do you see if you have a gravitational cat state in front of you? This is just developing non-relativistic n-particle system. The one-particle wave function comes in quickly. You all can recognize of the form of this one. The first term is of some interest because this term here is the mass density operator. So at the non-relativistic weak field limit, really the source term in the Einstein-Langevin equation reduces in the 0,0 component, basically, right, of the g mu nu, to the mass density operator here, indicated here. And we'll be focusing our attention on there. So here's a stress energy tensor. In this limit, right, it really is just the mass density. And you can work out one particle state. And so the mathematical expression of interest to us here is really the second line here, equation 18, okay? And of course, there's a green function, the two-point function in here. And I'll point out also something which distinguishes this as a uniquely quantum quantity in contradistinction to classical quantity. So that's the noise kernel, right, the C, right, which is the real part of the mu two-point function, the mass density two-point function. So really it's just connected two-point correlation function for the mass density, which is what we need to focus on. Thank you. Yeah. Okay, now these two-point functions actually are distributions, okay, by tensors. So it's ill-defined at one particular space-time, and you really need to introduce smeared function in order to obtain some physically meaningful significance of these quantities. So basically, just you know how to deal with, we all know how to deal with distributions. And then you can use the Wigner function, just like this is really an upgrade, right? I mean, the T mu nu, we know how to deal with it since the 70s for a long time. And here we're doing the same thing, except for bitensors, two-point functions. And the Wigner representation is an easier way to look at things, how things go. In fact, this would be a departing point. I originally had 3 slides here. I know I won't have time to show you, but maybe most of you are familiar with the Gaussian wave packet, for example, in the discussion of decoherence, okay, that you can actually use the Wigner function representation because it actually shows the distribution in a more pronounced way, clearer way, than just using the wave function. Suffice it to notice the quantum feature here, right? This is the quantum feature because if it's classical charge distribution. So notice this is all quantum, 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 right? Matter source. If you say that, well, it doesn't really matter, right, if it's already in this weak field limit, non-specific, we'll just do it classically. This is the difference. You would have the quartic power rather than the second power, okay? It's just like adding amplitude is different from adding probabilities. Just a few key features of correlations. Usually the fluctuations, at least for the 3 or 4 cases that we've looked at in quite detail, the fluctuations are of the same order of magnitude as the mean mass density. We have to pay attention to that. And it's highly non-Markovian. I pointed that out. It's color noise, non-local dissipation. And so if one takes the Einstein-Langevin equation and look at the non-relativistic weak field limit, one needs to be mindful of these properties because if you just look at the first one, it's not so easy to deal with these fluctuations. Okay, so let's move on. Skip this one. Gravitational cat state. Okay. I mentioned some of the numbers here. I'm sure people like Marcus, I don't know if he's still around, could tell me the more up-to-date numbers. So here's the cat, right, on the left and on the right. And we are trying to probe it with 2 kinds of probes. One is classical probe, the other is quantum. So we'll use harmonic oscillators, the ubiquitous tool. So let's consider a particle of mass m0 near the particle of mass m. Let's prepare in the cat state. So this is what we want to probe. And if you put a probe there, also, of course, mass is all gravitational here, right? You can easily work out this expression that there's the force, etc. This is freshman physics. No big deal. But what comes out, right, in the measurement, if you use a classical probe, you actually will get something like a quantum jump, okay? Because you can understand, you can either go this way or that way in terms of classical physics. You cannot go both ways, let's say. So that's why it's jumping up, down, and so on. And this is an indication of the non-Markovian property, right? When you look at the force-force 2-point correlation function. So that's where you begin to see, actually, the cat attributes, okay, if you prepare the state in a cat state. But the quantum probe is also is probably of more interest. And you probably can read all the fine prints here, but I'll just point out here's the system, here's the probe, and then the interaction Hamiltonian is given in this form where chi is related to the tunneling. So you know that this is a quantum system and there's a tunneling probability from the left to the right and coming back to the left. So it boils down to, again, just a 2-level system. A double well potential is something that you can give easily to an undergraduate to work out. What is interesting here is what the response in the quantum harmonic oscillator is. And in order to solve this, you cannot use small perturbation assumption because it loses the whole point of interest. If it's just perturbation, you would actually be just hovering around one state or the other, even though there's quantum attribute in it. But we did an adiabatic regime. You can actually do it, albeit without imposing the usual rotating wave approximation. So this is getting into some details that people in quantum optics are very familiar with. And so we use the coherent state representation, and then I'll just tell you the result. What goes on here is that we will actually be obtaining a Rabi oscillation of frequency nu between the 2 states. The nu frequency nu is the tunneling related to the tunneling rate. This is all intuitive, right? Because you can see that it's a quantum system and it's really a superposition of these 2 states, right? And as a result, there is a Rabi oscillation. Let me now turn to the last few minutes. In the implication of this, as I said, this is really probably the simplest case. Just right, 3 minutes. Yeah, thank you. the simplest case that you can come up with when you want to incorporate quantum information in a gravitational quantum context. Okay. Now, the standard interpretation. So I'm trying to warn people off just going down this easy road of non-restricted weak field, which is taken in a lot of the alternative quantum theories way, but really stick to the vantage point, the perspective of general relativity, that space-time and quantum matter are intimately linked, and quantum fluctuations of the force define the quantum fluctuation of space-time geometry. That statement is embodied in the Einstein-Langevin equation. Remember I said you have to solve the matter field and the space-time geometry self-consistently, not only now at the mean field level, but also going beyond, okay, beginning to take into fluctuations and correlations. And so if this is true, the state we consider here is genuine gravitational cat state, a quantum superposition of two space-time geometries. This harks back of what Roger Penrose sort of started his inquiry into this thing, which ended up, of course, in the well-known Diochet-Penrose framework. Because notice that the killing vector, let me just remind you what Roger was saying, right? As simple as just writing down an Schrödinger equation, and then you said well, it governs the state A, and then another one that governs state B. The ddt being a killing vector would actually pertain to different space-time. So already there you're talking about the superposition of two space-time geometry when you write down two innocent-looking Schrödinger equations for two neighboring states, right? And when you do the addition and all that, that's where the problem comes in. So here, does the gravitational force remain slave to the mass density as classical general relativity dictates? We've seen, of course, the quantum jump if you use a classical probe, right? And then we could ask, can we talk about quantum jumps on the gravitational potential? And notice that the gravitational potential really is an indication of quantum spacetime. Okay, so this little thing that we can deal with in the experiment actually has some deeper meaning to it. Gravitational decoherence, I talked about it last year, and that, of course, pertains to macroscopic quantum phenomena. And this is a good way sort of to get into the game and see the intrinsic tension between general relativity and quantum mechanics. So overall, the perspective as a summary, in view of the advances in AMO, condensed matter physics, and optomechanics, precision experiments in weak gravitational field that makes it possible and brings in all these important issues that we could actually see. Of course, I'm making this emphasis in contradistinction to going to the Planck scale and pretend that we know what's going on there. It's much better to do it this way. And the conclusion here is that the investigation of quantum information issues of gravitational systems using quantum probes, quantum gravity is not needed, okay? By quantum gravity, the definition is very simple. The theory for the microscopic structure of space-time at the Planck scale, we don't need it, okay? Even though I've been working on that, of course, since graduate student days, we should focus on systems under laboratory conditions. The second point is semi-classical gravity is inadequate. Okay, whether it's right or wrong, of course, there's some debate in it. You need to go beyond the mean field limit in taking into consideration fluctuations or the correlations. And now I'm posing a question to everyone. Okay, this was the request of the Galiano Island organizers to bring a big question. Can we infer attributes of space-time fluctuations from quantum experiments, even at the level of Newtonian gravity, without appealing to new theories of quantum mechanics or general relativity? Thank you.